Welcome to the fifth lab. In this lab, you're going to be introduced to ANSYS's fluid structure interaction. In this lab, you're going to have an example where we consider a T-junction that's subjected to thermal loads due to the mixing of two fluids, a hot and a cold fluid, with different temperatures. We're also going to take into account fluid pressure. In this lab, you're going to be using everything that you've learned in previous labs. We'll use ANSYS Fluent in order to get the fluid pressure that's acting on the inside of the T-joint. We're going to be using ANSYS steady state thermal in order to evaluate the thermal stresses. And then we're going to be using ANSYS static structural, which is going to give our complete structural result along with our safety factor. Now we'll discuss the boundary conditions in this project. On the left hand side, you'll see our hot and cold inlet that we're applying inside of the thermal boundary conditions. On the right hand side, you'll see the temperature profile that we actually import from ANSYS Fluent into steady state thermal. In addition to the thermal boundary conditions, we also have structural boundary conditions. In this case, we have three fixed supports, 1, 2, and 3, where the pipe T is held in place. In addition to this, we also have the imported loads which we bring in from the thermal and fluid simulations earlier. In this lab, we're going to begin from a previously saved ANSYS archive. To do that, go to File, hit Restore Archive, and then locate the archive that you are given on Blackboard. You'll hit Open, and then it'll ask you where you want to save all of your project files. In my case, I'm just going to save it to the same folder. So it's extremely important at this step that when you restore the archive and save the project directory, that you do this to a local hard disk. Do not save to the network drive. Do not save to a USB memory stick. Do this to the local hard disk on the machine that you're working on. If you do it any other way, you will encounter an error later in the lab. After you restore the archive, you'll see that a fluid flow fluent system is already present inside of your simulation. So what we've done is we've actually previously solved this fluid flow fluent simulation for you and just given it to you so that this way we don't have to repeat the previous lab in order to complete this lab. But note that typically when you do fluid structure interaction with heat transfer and structural mechanics like we're going to do in this lab, you first have to do the fluid simulation. You can check and verify your results very quickly to see what's inside of this simulation if you're interested. But you'll see that it is a pipe mixing T. And what we have in here is some fluid flow. So I'll show you a quick contour inside of the fluid domain of, let's say, pressure. So there you can see the pressure of the fluid acting inside of our body. Alright, we'll close out of here. Now what we want to do is set up our fluid thermal structural analysis. There's a few ways of doing this. The first one is what you're typically used to, of dragging all of the analysis systems into the project schematic and then linking everything up. But there is an easier way of doing it. You can simply click on Solution from Fluid Flow Fluent, right click, and then transfer the data to a new steady state thermal system. You'll see that it automatically creates all of the links for you. So as I mentioned previously, we're going to do fluid, heat transfer, and then structural. So click on the solution of the steady state thermal, right click, transfer data to new, static structural. And this links everything up for you from the steady state thermal to the static structural system. Now we have to perform one extra step, because when we're doing the structural analysis, we don't only have the thermal loads, we also have the fluid loads. So we'll drag the solution from cell A5 to the setup of C5. And then you'll see this additional link connected. So basically what we're going to have happen is that we're going to import the loads from our fluid flow into our steady state thermal system, where we're going to solve for all of our thermal quantities, let's say heat transfer. And we're going to take this solution and import that load into static structural, so we'll have thermal stresses. But we're also going to import the solution from our fluid so that we also have the fluid stresses on the body. Now after we're done with this, our next step is going to be to set up the engineering data. So we'll double click on engineering data to open up the engineering data toolbox. In the fluid flow, we use steel for our actual body. So what we're going to do is take this structural steel and we're going to copy it. So right click and duplicate and create a new structural steel. We're going to double click and rename it steel. Then click on steel. And we just need to set some properties here to be the correct properties for the simulation that we're performing. So the steel that we considered inside of the fluid simulation has a density of 8030 kilograms per meter cubed, and it has an isotropic thermal conductivity of 16.27 watts per meter degree Celsius. So we'll enter that 16.27 and hit enter. Everything else can be left the same. Now you can close out of engineering data. Now we'll start stepping through analysis system B, the steady state thermal system, step by step. We'll begin with model, so double click on model. This will start ANSYS mechanical. And once we're inside of ANSYS mechanical, we'll see a few things. The first thing we'll see is our entire geometry here on the right hand side. So you see we have our pipe mixing T-system with our flanges, our nuts, bolts, and screws. And everything is here. Let me, back to an isometric view. And then you'll see inside of our project tree that we have our model, everything that you're used to, but we have a steady state thermal system in addition to a static structural system. So everything is appearing here. Now we do like we've done in all previous labs, and we're going to step our way down the tree. We'll begin with geometry. So open up geometry, and you'll see that we effectively have three bodies here. We have the solid body, the nuts and bolts, and the fluid. So the fluid we learned from the previous lab. This was done by finding the volume inside of our CAD model. Now when we're performing static structural and steady state thermal analysis, we don't need the fluid. So we'll right click on it and then suppress this body. You should see an X appear here that the body is suppressed. We'll keep our nuts and bolts and our solid body. So the solid body is this exterior, and then the nuts and bolts are literally the nuts and bolts. One important thing to mention is you'll notice that this is cut along the XY plane down the middle. The reason that is because this is a symmetric simulation. So if you were to imagine fluid flowing through this pipe, the mean quantities of the fluid flow, the heat transfer, everything are symmetric about this plane. So they should be a mirror image of each other about this plane. This accomplishes two things by simulating it this way. The first one is that we don't have to generate a mesh for the entire body, which significantly cuts down on the number of nodes and elements that we use inside of our simulation. And in turn, the second thing this does is really cuts down on the amount of time we need for our simulation. Alright, so now we have to set our material properties inside of our geometry. I'm going to open up nuts and bolts. There's a lot of components here, so I'll start by clicking on the first one, part 27, and then shift clicking down through the bottom, part 26, so it selects everything. And then you'll see your definition. So here we're going to change the material assignment to the steel that we just created instead of the regular structural steel. Then we can minimize nuts and bolts. Now we'll open up solid. We'll click on the first part 2, shift click to the bottom, and then go to the assignment for material and change it to steel as well. So now we've set all of our material properties. We then need to step down to the actual meshing of this geometry. So I'll begin just to show you by generating a general mesh before we go and actually correct this mesh. Now you see by default it generates a mesh of tetrahedra here, and then you see quadrilateral or hexahedral elements in the upper and bottom regions. If we open up statistics, this goes well above our student license count, and we have a very coarse mesh on the center of this pipe. So we're going to work on a few refinements to make this mesh much better. The first thing we're going to do is right click on mesh, insert, and select method. Now by default it's set to an automatic method. That's why you saw two different element types on the two different parts of the body. However, we're going to specify that for the entire body we want tetrahedra. So we'll begin by clicking on geometry, then go to the right hand window, right click and select all. So this selects everything, and for geometry hit apply. So you should have 38 bodies selected. Then instead of the method being set to automatic, we're going to click, select the drop down, and select tetrahedrons. So I'll show you what this does. We'll update the mesh, and now you'll see that these are all tetrahedrons. All of the hexahedrons that were formerly up in this region are gone. Right away we see that our count went down a little bit. Now we're going to want to refine this mesh, especially in the middle region, but this is going to cause a little bit of problems, so I'll show you how to correct that. We'll start by just going to mesh again, go to sizing, and change the relevance center from coarse to medium. We will update, and you'll see that the mesh refines quite a bit. However, you'll also notice that the mesh becomes very fine, specifically on these nuts and bolts, much more fine than it needs to be. And that's actually problematic, because if we go down into our statistics, we are now above the student license limit. So what we're going to do is go to mesh, right click, insert, sizing. So what we're going to do is go to mesh, right click, insert, sizing. Now what you see right away is that we can change element sizes for specific bodies. In our case, we want to coarsen all of these nuts and bolts. Now, the difficult way of doing this would be to click on every single one of these nuts and bolts, which, if you remember in geometry, there are quite a few of them, and then apply the geometry. We're going to do this a little bit more easily. What we're going to do is go back up to nuts and bolts, open it up, and then click on the first one, shift click on the bottom one, right click, and create a named selection. We're going to name this nuts and bolts. Alright. Now that we have that, we're going to go back down to our mesh sizing that we created a moment ago. Change our scoping method from geometry selection to named selection. And then out of the named selections, we're going to go through the drop down list and select our nuts and bolts. Then we can specify an element size. We're going to specify 0.01 meters. And then we will update our mesh. Now you can see that we've coarsened our nuts and bolts, but kept the rest of the mesh nice and fine. We can also see that we fall under our student license limit. So our next step will be to move down our tree. We have our mesh done. We don't need to do anything here in named selections, so we'll move into steady state thermal. The first thing that we're going to do in steady state thermal is import our load. So click on import load, hit insert, temperature. So this imported load is actually the temperature of the fluid from the previous fluid simulation that was already performed for you. And we're importing the temperature of the fluid as it's going to be imparted on the wall. Now in order to do this, we're going to have to select our scope, where everything is in contact. Under scoping method, you'll see geometry. Change this to named selection, and then select interface solid side. So this is a named selection that we already created earlier of the inside of the pipe. So if I rotate around here, you'll see in red that all of these faces are highlighted. That is the named selection interface solid side. Now the transfer definition is the load that we're bringing in from the fluid data. This is the CFD surface. So you will click from the drop-down menu. You're going to select interface fluid side. So what we're saying here is that the fluid side is touching the solid side. Once you're done with that, go back up into the tree, right-click on imported temperature, and hit import load. Once you're done importing your load, you'll see inside of this screen that you can now see the temperature contours that we're bringing in from the fluid simulation on the inside of the pipe. Pretty nifty, huh? Now we're going to do a quick sanity check just to make sure that everything was imported all right. You will click down here next to imported temperature, and then click on Imported Load Transfer Summary, and you'll see a comment window appear. What this is telling you is that from the CFD data, the average temperature is 57.615 degrees Celsius, and then after you imported it onto the interior of the surface, you reached an average temperature of 57.532 degrees Celsius. These two numbers should be close together, because remember that the mesh that you used in Fluent is different than the mesh we just created here. And we're interpolating data between these two meshes. You want to make sure that they agree sufficiently well. Alright, so that is the end of importing our load. Now we make a few other assumptions here. I'm going to go back to an isometric view. We have to set a few other thermal boundary conditions. The first one is going to be our convection that's occurring on the outside of this entire piping system. So we'll insert convection, and for our geometry selection, we're going to switch this to a named selection. We have already pre-made a surface for you called convection that includes all of the exterior surfaces. So you can just select that. And these are all the faces where the convection is occurring. Now you notice that this does not include the nuts and bolts, and this does not include the ends, because this is actually a pipe that continues going on far, far off into the distance, so there's no convection there. And these little regions that have no convection, because this is where we're going to have coupling. We're effectively going to have our structural supports at this location, so they will not be exposed to the air. So we'll go back to our convection definition. We're going to set our film coefficient to 10 watts per meter squared. Please make sure that this is watts per meter squared degrees Celsius. If you have watts per millimeter squared, you will get the wrong answer. And then set the ambient temperature to 15 degrees Celsius. That's what we'll assume our external temperature is. Now, as I mentioned previously, we also have temperatures of these pipes that are extending on into the distance. So we'll insert a temperature load, and we will make the assumption that the temperature at these locations on the pipe is the temperature of the fluid far along this pipe. So if you just go to scoping method, named selection, we'll begin with the wall hot end, and we will set the hot end temperature to 80 degrees Celsius. And then you can see our hot end temperature here at the bottom will be 80 degrees Celsius. Then we'll insert another temperature boundary condition, change to named selection, and we'll select our cold end. And for this boundary condition, we will make it 20 degrees Celsius. And then you can see our cold end is right here. So we have a hot end here, a cold end there. We have the interior fluid, and then we have the external convection. Now just to clarify why we set it this way, I'm going to go back to the imported temperature. So you can see here that the cold fluid coming in is at 20 degrees. The hot fluid coming in is at 80 degrees centigrade. So we're just making the assumption here that this pipe, because it had cold fluid running in it for that distance, has a temperature of 20 on this surface. And the hot pipe, which has had fluid running through it at a temperature of 80, will also be 80 at this location. And then that defines our thermal loads. Once we're done setting all of these thermal loads, we'll just go to Solution, right-click, and Solve. This will take a short moment, and when you're done, you'll have your solution. So we will insert our thermal temperature, right-click Solution, insert our thermal total heat flux, and then right-click, evaluate all results. This is just like we've done in all of our other labs. I will go back to an isometric view, rotate it around. So here you can see our steady state thermal heat flux. If we click on temperature, you can see the temperature distribution inside of the material of the mixing tea. Now we're done with our steady state thermal portion. We'll move on to structural. So once we're complete with our steady state thermal, we're going to want to close out of mechanical. The reason for this is because if you remember, our solution is being imported from two places. And you saw on the screen that we had both steady state thermal and static structural, but your loads from Fluent wouldn't be imported unless you move to this step in Setup. So double click on Setup in Static Structural to reopen Mechanical. When you take this step, it should import our loads from Fluent in addition to what we've done in Steady State Thermal. So now when you go down in Static Structural, you'll see that you have two imported loads. If you only have one, close out of Mechanical again and make sure you follow the correct step of opening Setup from Static Structural. Once you're under Static Structural, first we're going to import the body temperature, just like we did before, and hit Import. Mine has already been imported. If yours has not, simply right-click Import. Then we want to import our load from our CFD results. So I will right-click, Insert, Pressure. So this will be the pressure from the fluid being imparted into the inside of the mixing tea. Just like we did before, our geometry will be a named selection, and that named selection will be the interface of the solid side. The CFD surface will be the interface of the fluid side. Once you're done, right-click, Import Load. Now if I rotate this around, you will see the pressure vectors pushing on the inside of the pipe or pulling on the inside of the pipe depending on their location. So that will be our pressure load, and everything will be normal to the pipe on the interior of the pipe. If I go up and click on Imported Body Temperature, then you'll see the temperature inside of the pipe. So when we perform the static structural simulation, we'll have a few things happening. One, we'll have the thermal strain of the expansion and contraction of the pipe. Then we'll also have the imported pressure of the fluid inside pushing and pulling on the inside of the pipe. The final thing we have to add is our supports, because this thing isn't floating in space. So we'll right-click Static Structural, hit Insert, Fix Support. We're going to rotate my pipe around. Now there are three areas on the pipe that we've created for where the supports, imagine them as effectively bands, are connected. First one is on top here, then Control-click the second one on the bottom here, and the third one is this far lip on the right. So after you Control-click those three surfaces, hit Apply, and those are your supports. So what do we have at this point? A mixing tee that's held at these three locations with a body temperature along the entire pipe and an imported pressure of the fluid inside pushing and pulling. Once you're sure to have all of these, then you can right-click on Solution and hit Solve. Now once it's complete, we can insert our solution. So we'll start with total deformation. We'll also insert von Mises stress. And then the last thing that we'll insert is our stress tool. Then you can right-click Solution and evaluate all results. If you click on total deformation, you should see the deformation of the pipe. It deforms pretty funny. But you should see that the contacts where we place the fixed support are fixed. They should have no deformation. This is a quick sanity check. Now it appears really bad, but if you look at the actual maximum deformation, it's about 9.5 times 10 to the negative 5 meters. So that's relatively small. We can take a look at stress and see where our stress concentrations are. So you see this is happening in a few locations. Right here around the pipe, around where the bands are applied, and along the exterior near the bands are. And then finally, under the stress tool, we can take a look at the safety factor, which is not good. 0.54, sub 1 safety factor. Some places are 15 or greater. So please note that if you see a safety factor of 15 in ANSYS, that is the maximum safety factor it will give you. If you calculate the safety factor by hand, which you can very easily do, right? If you know the von Mises stress and you know the yield strength of your material, you can calculate safety factor. It's in your ME380 book. You'll see that it's actually greater than 15. But ANSYS does not calculate it beyond 15. Greater than 15 is a huge safety factor. But we do have regions where the safety factor is 0.5 in our concentrated stress regions. So do you think this design is good? Now we'll close out of mechanical. and we'll see an overview of what we've done. We began by performing a fluid flow simulation, which we then imported the data into a thermal simulation. We took the data from the thermal simulation and imported it into a static structural simulation. Then we also imported the fluid flow data into the static structural simulation, where we took a look at the structure under the effects of thermal and pressure load from the fluid. We were then able to make a design decision based on the safety factor, von Mises stress, and total deformation that we saw inside of the mixing tea. So this is how you would use ANSYS in a real-world case. Up to this point, you've seen everything done in small units. Now we have this final lab where we see everything come together, and you can perform a complete simulation on a system where you can make an educated design decision based on all factors of simulation. That is the end of this lab.